In this video, we're going to look at how to do loads and stores in ARMv assembly, and I'm using the GNU assembler. So some of the things that we'll talk about are specific to the GNU assembler, in particular some of the directives like .global. All right. So let's say we have this problem. I want to store in register 1 the number 0x, that's 0x12, which is a hexadecimal number, and this number as well. And I'm also going to write it as hexadecimal, A, B, C, D, E, F. So that's a hexadecimal number. Let's see what happens when I attempt to assemble it. So AS-G for the debugging information, -O to indicate the output object file name, and the source code is code.s, and it's giving me an error message. And what the error message is about is that this number right here is too large to be part of the encoding for this entire instruction. Okay, the first one's not, and we can see that. So let's comment out this line and now try to reassemble it. So it assembles. Let's link it, and now let's use object dump to disassemble the executable. And so it turns, you can see what it writes here, that the hexadecimal number 12 is the decimal number we call 18, but this right here is the machine instruction for move R1 0x12, but it's written in hexadecimal. So the 12 that we see down here is this 12, although it's not decimal 12, and then the 1 here is associated with this being register 1. So this is part of the 32 bits. This value here is part of this 32 bits. But this number is too big to do that. So let's see what we should do instead. I'm going to create a data section. So this is a GNU assembler directive, and this is saying that what I'm about to write is data, whereas this is code. And this would technically be the text section. So I need to give it a label. Let's call it big. And to store this, I want to allocate 4 bytes. So I'm going to say .word, which is another directive. And let's take this number and put down here. Except now I won't use the pound. So it's still a hexadecimal number. And now what I'm going to do is this. I'm going to say load register R2, comma, equal big. And this is called direct addressing. And if you are familiar with the C programming language, this is kind of like saying int star A, or excuse me, P is equal to &A. That is, get the address of some integer and store it in this pointer to an integer. And next we're going to do this. I'm going to say LDR R3, comma, square brackets R2. This is indirect addressing. And once again, in C terms, this is kind of like saying if we had some variable X, that's equal to star P. That is, I'm taking the address stored in R2, and the square brackets say get the value at that address, and now load that in register 3. So now let's try to assemble that. Link it. And now I'm going to use the debugger to look at everything. So a.out, set a breakpoint, run it, look at the registers. And let's do this first. Let's examine this memory location. So examine slash, it's word sized, and I'm going to look at it as a hexadecimal number and use ampersand big to say this is the address I want. If I knew its actual address, I could just put the address there, but I don't. And so its address is the hexadecimal number 2008C, and we can see this is the number we have there. So let's continue to step through. Okay, so look at what it did. It loaded into R2 that address, 2008C. And now we want to get the value at that address, and there it is, A, B, C, D, E, F. So what is happening here? Let's look briefly at this model here. So we have the register file, which has our different registers, and we have memory. So if we have something like this, if I have variable, say B equals 5, and C equals 10, and I want to produce A equals B plus C, in a load store processor, we'd have something like this. We have B here with value 5, and let me put it right here to make it easier. C here, we'll say 10, and we want A to store the answer. So what we have to do is we have to load what's in B to a register, load what's in C to a register. Basically, technically, we had the arithmetic logic unit, so these values would get transferred down here and produce 5 plus 10 equals 15. The 15 would get copied back. Okay, so we would do an add for this. And then we store what's in R2 to this memory location. So that's basically what the process is. So there's several different ways to do indirect addressing. Let's look at those. So this right here, and let me go ahead and finish this. This got the value stored at the address in R2, but it doesn't do anything to R2. There's many times though we want to use this as maybe a base point, like this address if I have an array. Let me go down my code and we're going to change this a little, do something else. Let's call it array to make it meaningful. And now I'm going to put these numbers in there. So each of these consumes 4 bytes because of the dot word directive. So we're going to do LDR R1. I can choose any of the general purpose registers equals array. R2. Okay. And now let's do this. Let's look and see what happens. Let's examine that memory location. So X slash, I want to look at 4 words in decimal at this address. And there they are. So the address is 2008C like it was before. But what's meaningful here is here's those 4 integers. I'm going to step over here. We just got the value at 11 that was in R2. But we didn't change R1. But now what's going to happen? Let me save this. Now what's going to happen is I'm going to take the value stored in R1, add 4 to it as an offset, and then get its value, which should be the 22. So let's step and see if that's what happens. Yes, so there's our 22. Okay, I didn't change R1. All I did was, it was like a temporary thing. I took 4, added it to this address, got the value at that new address, but I did not change R1. Let's go ahead and quit this. Many times though, we will want to move on to the next thing. So in fact, let's do this. So this is indirect addressing with what's called a writeback. So what does it do? It says R1 plus 4 is a new address. The exclamation mark says save that into R1 and then use it. So this is the pre-indexed version, or excuse me, pre-increment. Update R1 before you use it. But there's times though that we want to do this. So let's redo R1 here. There's times we want to do post increment. So what does this mean? This one doesn't need the exclamation mark. What it says is get the value currently pointed at by R1, store that in R2, and then afterwards add 4 to this address and save it to get a new R1. So if you think about it like how you'd move through an array, processing elements, let's say we do this. Let's look and see what happens with each of those. So what happened? Why did I skip the 11? Well, remember, we said right here, add 4 to R1, save it. And so we used the new address first. So we, even though R1 was pointing here, we added 4 to it to jump to here, and then that's the value we got. Now for this one, I'm going to get the address of the 11 again, just like I did here. But then I'm going to use it before I add the 4. So let's see what happens as we continue to step. So I've reset the address. Is that what we had before? Let's look and see. It's not. It doesn't have to be the same, actually. So C2009C is the address now for the beginning of the array. Now I'm going to continue to step. So now I got the 11, but the address changed. See, it went for A0, which is 4 past this. So I get the next value, next value, next value. Now, what about stores? We talked about that. With stores, we could change each of these, or these actually. So it'd be like store, store. Well, let's not do that one. Let's do this one, change store. I can change these, and so basically the idea is this. When we have a load, let's write in capital, even though we'll have to, it's destination so with the load, I'm saying, here's my source, and transferred to here. With store, I'm saying, here's my source, transferred over to here. But we still can do these things to change values. Let's demonstrate that. So I'm creating 2 arrays, and now we're going to introduce something new, space. So what does this do? Well, what this is going to do is allocate 16 bytes of memory, because since I have 4 ints here, I want to do something with each of those 4 ints, and I'm using C terms. It's actually 4 integers, each of which uses 4 bytes because I'm using .word. So I'm allocating the same amount of space used for this. So let's do this in our logic. We'll get the address of old and put it in R1. Get the address of new, put it in R2. And now what I want to do, let's load into register 3 the value at R stored in R1, and then increment to the next value. I'm going to add 100 to that. And now store that, what's in R3, into the address stored in R2. So basically, I'm going to take 11, add 100 to it, put it in this spot. Add 100 to this, put it in this spot, and so forth. And to continue this, I need that also to increment. And this would normally be in a loop, but I'm going to make it very explicit. So let's just copy these lines. We'll just do it a couple of times. So this should do it, move to the next position, do it, move to the next position, this. Oops. And it's telling me my label needs to be fixed. So close, and then GDB, a.out. Now let's look at our 2 spots. So I'm going to do an examine. for WD of old. That's what we expect. And let's see about the other. For WD of new. So what the space command does is it zeroes it out unless we give it a value to fill. So if I had done this, it would put a 5 in each of these bytes, each of the 16 bytes actually, not the 4 integers, but the 16 bytes would each have a 5 in it. But I don't want to do that. So let's continue. There's the 11. Change it to 111. Write it back. 22. Change it to 122. Write it back. 33. Change it to 133. Write it back. And let's see now what we have. We'll look at old again to make sure I didn't change anything. Look at new. And there it is. And we could continue to put the 44 down here with some value. Now let's also point out something. Notice here that I used Word. I could have used something like this, dot byte. In fact, if I change that, now I still can store these 4 numbers, but each one only consumes a byte. But if I did that, then when I get the values, I would need to make this a byte. And likewise, if this right here, say if I said I was going to allocate only 4 bytes to have the new values, then my stores, each of these would be a byte. And you also can do half words. So I can use .h word for half words, and then these would be an H to write 2 bytes at a time. But anyway, you just have to make sure that you know how many bytes are being used for your type. When I had Word, Word means that each of these is stored in 4 bytes, so I would just use a regular LDR like here and a regular store like here. But anyway, that's the basic idea behind loads and stores.